Welcome back to the home lab, and looking a bit smarter today because I've been out teaching maths again. So I've got a really interesting video for you today. What we're going to look at is the concept of chirality using just 2 apples. Just before we start, I want to say an absolutely huge thank you to all for watching my little channel, and the fact that we hit 7,000 subscribers this week. The numbers just leapt for no reason that I could really see. One particular video people were enjoying on the electron mirror. Also to PCB Way, who sponsor me and encourage me to make these videos. I'm sure you all know they make printed circuit boards, they do CNC machining and 3D printing, but they've got a really good tab on their webpage on shared projects, and I suggest you go and have a look at that because I'm sure you'll find something that will give you inspiration for a project that you'd like to do. So let me show you how to make a chiral apple, and I often get this wrong first time, so let's see how we get on. So let's get rid of the stalk because I'm going to find it tricky to cut that in half. Now the trick is you need to cut halfway through that way, halfway that way from underneath, and then a sideways cut here and a sideways cut there to join the 2 parts. So that sounds easy enough. Let's have a go. So I'll put the apple like that. So I'm going to cut halfway through it and stop. Okay. And then I'm going to turn it over and cut halfway through it in this direction, so at 90 degrees. There we go. So that's the first stage done. So we're halfway through in that direction, and we're halfway through in that direction, and then what we've got to do is join that bit there. So I'm going to cut that way. There we go, and you can sort of see a bit of a sort of funny shape forming there. Not cut that bit off, but find the next part where you get a cut going this way and that way, and join those 2 as well. I think for once this is going quite well. Well, we'll see. And then the fun bit is when you separate the 2 halves. But to show chirality properly, you've got to repeat that process. So you've got to take a second apple, cut that way. I know I'm going to get it wrong if I do this. Turn it over, turn it through 90 degrees. Cut it that way. Okay, join it that way. There we go, so that's that joint done. And now I've got to go round, round, round and join this bit. What's the chance of this actually working? Oh, look at that. Prise them apart. That's the best I've ever done it, actually. There we go. And then what we're going to try and do is see if we can fit one side of one apple with a sort of corresponding side of the other apple. And I think you'll be surprised by what happens. So here are my 2 cut apples, and if I've got this right, when I prise them apart, something really interesting is going to happen. So here we go. Look at the shapes I've produced. They're really quite an intriguing shape, and you'll notice they perfectly go together. Now I cut the other apple in exactly the same way, and I prised this one apart. So there we go, these interesting little shapes. So yep, this it just doesn't seem to work. They seem to be handed and they're not superimposable. So these are chiral apples. So to explain what's going on here, you need to know a little bit about chirality. It comes from chir, the Greek word for a hand, and you'll see why that's a good choice in a minute. So the first thing to look at is an achiral object. Now an achiral object is one where if you take the mirror image of it, its mirror image is indistinguishable from the original object. The example that's always given is that of a shiny steel ball bearing. That if you were to reflect this in a mirror and then slide that reflection across on the original image, you can't tell the difference. They look identical. But a chiral object behaves completely differently. Now chiral objects have a really interesting property. They're mirror image non-superimposable, which means that if you take the mirror image of the object and then slide it on top of the original, they are distinguishable. You can see differences. They are enantiomorphs. Okay, so that's Greek. Enantios means opposite and morph means forms. Now the classic example that's always taken is human hands. I know it's back to front for you, but this is my right hand and this is my left hand. And if you can imagine, I take my right hand and I put a mirror here and get a reflection of it. I don't get that. Okay, I don't see the rear of it, I just reflect it over. So it's as if the mirror there reflects over to this side. But the interesting thing is, if I then take those two and lie them on top of each other, they don't lie on top of each other. They're not mirror image superimposable. So the human hands are an example of something that is chiral. Now, chirality is really important in chemistry because you can have molecules that we call isomers that have identical atoms in them, identical bonds, but they're arranged differently. So they look the same, but in fact, they're mirror images of each other. They won't lie on top of each other. They're stereo or optical isomers. And the way you'd find out that they were optical isomers is you pass light through these in the liquid form, and it does something really interesting to the plane of polarized light. Now, I said our stereoisomers do some really interesting things with light, and you'll notice that these two are definitely mirror images of each other. So what we're going to do is we're going to take one of these and make it into a liquid, put it into a liquid. If you can imagine a tube going towards you with a light source back here and a polarizing filter behind it. So that allows the light to wiggle in one particular plane, maybe in the vertical plane. Now, at the other end, the bit that you're viewing, you also have a Polaroid filter orientated in the same direction. And in fact, to see light come out of this, you have to rotate it slightly. So what's happened is the optical isomer in the liquid in the tube has rotated the plane of the polarized light. And there's a convention here based on glyceraldehyde that if viewed looking at the light source, if it rotates in the plane of polarized light in the clockwise direction, we call that plus or dextrorotatory, and in the anti-clockwise or minus livo-rotatory. Now, if you mix the two, obviously you're going to sort of cancel out the effect. But if you've got one in there, one of them will rotate the plane of polarized light in the anti-clockwise or the minus direction, and the other stereoisomer will rotate it in the plus or clockwise direction. So you can distinguish optical isomers by shining plain polarized light through them and seeing which way they rotate that plane. But why does all of this matter? Well, it matters a great deal in chemistry, and I'm just about old enough to remember the problems with thalidomide. If you've heard of thalidomide, it's a drug that was given to pregnant women to help them with morning sickness. And there was a problem with the manufacture of thalidomide in that it had two different isomers. And if I remember rightly, the one that was described as a left-handed isomer was perfectly safe and helped women with their morning sickness. But the right-handed isomer was really toxic, so much so that it led to a huge number of very serious birth defects with children. Now, there are less devastating effects of getting the chemistry wrong here. Humans, in fact, can respond to chiral molecules in really interesting ways. We can actually separate them through taste and smell. And the one I always remember being told about when I was younger was spearmint. You've got a chemical called carvone in there, and carvone comes in two optical isomers, so a left-handed and a right-handed one, and one of them gives the taste of spearmint, which is quite a fresh sort of taste, and the other one is caraway. And caraway, exactly the same molecule but an optical isomer of it, has a much sort of spicier and stronger taste. You might want to give that a try. I think that's a perfectly good experiment to try, and I seem to remember when I was a kid them handing out a bit of spearmint and caraway seed, I think it was many years ago, and you tasted them and smelt them, and they tasted and smelt different, and yet the lecturer said, do you realise they're absolutely identical molecules? So I do hope you enjoyed my video on chirality, and especially the chiral apple. Why not have a go at this? Do it carefully because you're using a knife, but it's quite interesting and they're quite nice to serve up to people. I think it's called the coupe royale, I think the royal cut, but I don't know any history of that. Have a look around you also for other chiral objects that you might see around the place. Have a look for the tendrils on plants that kind of spiral or helix up one way, or seashells that rotate in one direction or a different direction. You might, of course, want to take a picture of your face and then take one half of your face and flip it over and join those two bits together. So join two right-hand sides, as it were, the right-hand side and the mirror image of it. And I think you'll find you look completely different. You have a chiral face, a right-hand side and a left-hand side that look different. Anyway, at the end of my video, do stay to the end because I often put a few extra bits in, and I put some links to other interesting videos right at the end. But I'm bound to be making something else fairly soon, so do please join me then.